So here's a quick review of the solutions to AP Review number 1. Again, all the answers in the breakdown are found at the end of the document. It's a little bit weird because they do it two different ways, the general solutions and then maybe some acceptable specific examples. But scroll through them and you can figure out what is acceptable and what isn't. Okay, so I'm just going to talk about some highlights of this problem. So I chose this problem first because it gets into some data analysis, even though it's fairly straightforward. The fact that it's simple harmonic motion more than anything is beside the point. Okay, so, and waves. Anyway, so we have an oscillator where the string gets thicker and thicker, heavier and heavier. All right, so they were asking which will have the longer wavelength. A good question because it asks us to understand the difference, a relationship amongst velocity, wavelength, and frequency. So the answer is the left half. Why is that? Well, the left half has a higher speed. Okay, it has a higher speed because you're told so. What is the same for both is the frequency. So the frequency is the same because it depends on the oscillator. So we have a wavelength here that's going to equal to V over F, and I'm going to call this lambda prime, which is going to be V prime over F. F is the same for both. This speed is smaller than this speed, so the left side is going to have a longer wavelength. So you need to get the right answer for one point, and then you need to have a coherent explanation for the second point, and that's shown in the key. Okay, so let's go to the next one. Next one is the toughest one. I'll tell you right now, the answer they give is not something I would have thought of. I would have taken a different approach, and upon thinking about it, I understand why that approach wouldn't necessarily work. So I'm going to say the approach that I would have thought would have worked. And they're given a velocity time and they want amplitude. I would have said, okay, the amplitude is related to the maximum elastic potential energy, which can be related to the kinetic energy. And this we would recognize as perhaps 1/2 Ka squared. There's our amplitude, 1/2 mv max squared. Okay, that's supposed to be an m for max. And then we say, okay, we go get the V max and solve for A. But the problem with that is we don't know the K value for the string, nor do we know the mass of that point. So that really doesn't work out. So that's a good problem if it's a mass on a spring, the amplitude of it. But for this case, on a rope, we have to take a different approach. And this is almost a kinematics equation, a problem, in the sense that we have velocity here and time there, and they want a displacement, because that's what amplitude is. So if you understand that amplitude is a displacement, then what might come to mind from something learned way back in the beginning of the year is it would be the area under this graph right there. You don't have to actually calculate it. You just basically say, and this has to be 3 points. 1 point for saying, hey, would find the area, okay, then 2 more points for a specific area. You could say find the area for a quarter of a cycle and then specify that the quarter of a cycle is between 0 and 0.1 or 0.1 and 0.2. It doesn't matter which pulse that you choose there. So that's a subtle problem. Not a bad idea to go with this, so I'm not sure if you'd get 1 point for that idea or not. There is an alternative they do there where you could make the relationship say that V max, okay, is related to the angular speed. Okay, in other words, we have oscillation, so there's an angular speed, all right, in anything. And what is the relationship between velocity and angular? Well, if you go back, omega is V over R, so V would be omega R, and R in this case would be the amplitude. And so you could say that the angular speed is nothing more than 2 pi f, which would be 2 pi over the period what we know, multiplied by A, and then you could use that. Okay, so let's move on. Next problem I think is a little bit more straightforward. Now we're in part B. So we're doing a completely different problem. They give us some information and they want us to find the wavelength to the left of C. So the idea is we want to use the wave equation. Lambda is V over F. F is given. That's 50 cycles per second. Okay, so you just have to figure out the speed, and you can do that using kinematics. In other words, we know that the pulse travels 0.75 meters, and it takes this amount of time, so that's really just some distance. I'm going to call x divided by t, okay, divided by the frequency. So it should be pretty straightforward for that one. All right, now we get into the analysis part, which is why, again, I chose this problem. Okay, let me see if I can get the scroll. Okay, so you have to do a bit of reading here, and that's important that you take your time to read things carefully, because this is not an overly difficult problem. So now we're creating a pulse that travels along here, and they hypothesize that the pulse depends on the diameter of the string d, and they come up with this equation. And we don't know if it's true or not, but we want to go with it. So they asked, is the equation consistent with the observation the pulse slows down to the right half? In other words, when it gets to this thicker part, the idea is it should start slowing down. Well, what do we have here? Well, our variable here, y variable is v, our x variable is d. We see that from this that equation is suggesting v is inversely proportional to d, and that definitely would support the assertion, okay? Bigger, and so you just have to explain that. You could say an inverse where a larger diameter gives you a smaller speed. And then they do some analysis. Oops, sorry about that. I have a hard time using this scribble on this. Okay, so does this support the equation above? And yeah, it's for the same reason. Again, our y-axis is v, and we have d on the x-axis. This should recognize as an inverse curve, so that supports v is proportional to 1 over d. And you basically give the same reasoning as before. Okay, so just the ability to recognize an inverse curve and relate that to 1 over the variable in question. My last question now, the solid line represents a pulse. To the right of C, they want you to, on point Y, draw a pulse that when it reaches point Y. Okay, so we want to, this is really, so you're going to draw a sketch. This is just built off of the first question, part A. Okay, and then when they asked about the wavelength, oh my God, I'm going to lose my mind with this scroll button, scroll bar. Sorry about that. Give me a minute. So if we go up to the diagram, here is the original pulse, and we want to draw the new pulse at Y. We said before that it should be a longer wavelength, so you just basically drew something that's longer. You don't have to worry about the amplitude or anything like that. And so that's the simple solution. Okay, so if you have any specific questions, message me.